Section 3.3 looks at systems of equations in three variables. So again, these are systems of linear equations in three variables. And linear just means that all the variables in the system are raised to the first power. One thing you should notice about a three variable system is, of course, there are three variables, in this case x, y, and z. The solution to this system will be an ordered triple in order x, y, z. And also, to solve a three variable system, you have to have three equations. So the number of variables must equal the number of equations if you are to get a solution. Now, the methods used are very similar to the two variable system methods that we used in the previous section. And so we're going to start off by looking at how to solve these using elimination. So the first thing I'm going to do, just for reference, is I want to label each one of these equations so that we can talk about them. So the first equation we'll call equation number 1, second equation is equation number 2, and the third equation is equation number 3. If I'm going to use elimination, I can eliminate any variable I want, and so it makes sense to choose the easiest variable to eliminate. So if you notice in the first equation and the third equation, we have a positive 4x and a negative 4x. If we add those two equations together, the x's will eliminate very easily. So that is going to be one of the eliminations that I want to make here. So equation number 1 is going to be added to equation number 3. And equation number 1 is 4x minus 3y plus 5z equals 23. And equation number 3 is negative 4x minus 6y plus 7z is equal to 7. And I'm going to add those together. And when we do that, the x variables cancel out. And we get negative 3y plus negative 6y is negative 9y. 5z plus 7z is positive 12z. And 23 plus 7 is 30. So by eliminating the x, you can see now we have one equation that only has two variables. All right, well, we can't solve an equation that has two variables unless we have two of those equations. So what I need to do is eliminate the x variable again using a different equation. So if we already used equations 1 and 3, the second time I eliminate the x variable, I must use equation number 2. So when I use equation number 2 to eliminate the x variable, notice that we have a 2x here. I'm going to either pick equation 1 or equation 3 to eliminate that variable. I'm going to pick equation number 3 because it has a negative, but this is negative 4x, and if I add that to 2x, those x variables will not cancel out. So what I need to do is multiply the second equation by positive 2 to make 4x here. So what I'm going to do is take equation number 2, I'm going to multiply it by 2, and then when finished, I'm going to add that to equation number 3. So here goes. Multiplying equation number 2 by 2 means we're going to take the second equation and we're going to multiply both sides by 2. And then we're going to add that to the third equation. Okay? Now there's one step that we need to do before we actually add. We need to go ahead and multiply that second equation by 2. So we need to distribute here. When we do that, that gives us 4x minus 10y minus 6z equals 26. And then equation number 3 remains unchanged. And these are the equations we add together. Now when we add, you can see the x cancels once again. And negative 10y minus 6y is negative 16y. Negative 6z plus 7z is z. And 26 plus 7 is 33. So now what we have is one equation here with the variables y and z, and another equation over here with the variables y and z. And those two equations make a new system, a smaller system. So if I bring those two equations down here, we get negative 9y plus 12z equals 30, and negative 16y plus z is equal to 33. Now we can use either substitution or elimination to finish this problem. I think I'll go ahead and stick with elimination because it is already set up for elimination. One note that I want to make here is that in the first equation, since all of these numbers are divisible by 3, you could divide them all by 3 to simplify that equation before moving forward. You don't have to do that, but I actually think it's really advisable. That way you can simplify the numbers, make them a little bit smaller. So I'm going to basically take this equation here and multiply both sides by 1/3, which is the same as dividing by 3. And that will give us negative 3y plus 4z is equal to 10. Okay, so again, I'm just multiplying each of these by 1/3. And that second equation is still the same. And now to finish this up, what I need to do is pick a variable to eliminate. This looks rather unpleasant, but I can cancel the z's quite easily by multiplying the second equation by negative 4 so that we have a negative 4z here. So let me multiply that second equation by negative 4. And this will produce the following. Okay, so now you can see we are ready to add these together. When we add those, the z now will also cancel out. And we end up with 61 times y is equal to 10 minus 132 is negative 122. Divide both sides by 61, and y is equal to negative 2. Now, once we have solved for one of the variables, we need to work our way backwards to solve for the other two variables. So once I have y equals negative 2, I can take that value and plug it back into one of our two variable equations. It doesn't matter which one. I'll just plug it into the closer one here. And when I plug that value of y into here, that will allow me to solve for z. So let's go ahead and do that down below here. So we have negative 16 multiplied by y, which is negative 2, plus z equals 33. This is 32 plus z equals 33. And that, of course, means that z equals 1. So we now have a value for y and a value for z. So the last value we need to get is x. And to solve for x, we have to go back to the beginning of the problem and use one of the original equations. And I'm just going to use the first equation, which is 4x minus 3y plus 5z equals 23. Let's write that down here. Okay, so here is the first equation. Now we're going to take the value y equals negative 2 and z equals 1 and plug each of those in simultaneously. And that will give us 4x minus 3 times negative 2 plus 5 times 1 equals 23, which is 4x plus 6 plus 5 equals 23. And then we just simplify and solve. And we end up getting x equals 3. Now we take all three of those numbers, x, y, and z, and we write them down to form an ordered triple. So x is 3, y is negative 2, and z is 1. And this is our solution. Now, I just want to point out that this is not a particularly difficult procedure, but as you can see just by looking at the work that we've done, it's pretty easy to get lost in all the different steps. So you have to be really organized and really neat when you solve these problems so that you can keep track of what you're doing. Let's talk about another method. So for our second example, you can see that we have another 3-variable system. This time the variables are A, B, and C, and our solution will be an ordered triple A, B, C. And I want to talk about how you can use substitution. So to use substitution, it's very similar to using substitution in a 2-variable system. Basically, what you need to do is pick one of the 3 equations and solve for one of the 3 variables. So what I'm going to do is pick the third equation, and I'm going to solve for C, because solving for C is the easiest variable to solve for. And if we do that correctly, we should end up getting C equals 9 minus 2a minus b. Now the next step is I'm going to go ahead and make the substitution C equals 9 minus 2a minus b, and I'm going to substitute that into both the first and the second equation. So here are my equation reference numbers. So again, we took equation number 3, we solved for C. Now I'm going to take equation 1 and equation 2, and we're going to substitute that into the first equation, replacing C, and also the second equation, replacing C. And when we do that, we get, for the first equation, A plus B plus 2 times 9 minus 2a minus b equals 7. And for the second equation, we get A plus 2b plus 9 minus 2a minus b equals 8. And so we're just replacing C with the expression that we got from the third equation. Now it's a matter of simplifying. So we're going to distribute. 2 times 9 is 18, etc. Make sure you're very careful when you do these steps. Then we're going to combine like terms. So I'm combining the A take away 4A and the B take away 2B. And finally, I'm going to subtract 18 from both sides. And that gives us negative 3A minus B is equal to negative 11. And then I do the same thing for the other equation, which is a little bit easier because there's nothing to distribute. And then solve. Well, get the a and the b on one side, get the number on the other side. Okay. And now you can see we now have these two equations, which only have a and b together. So now if we put those two equations together, I can solve this system however I want. Now, I'm not going to continue to use substitution here. I could, but look what we have here. We have a bit of a gift. If we add these together, we can see that the negative b and the positive b will cancel out. And that will give us negative 4a equals negative 12. And dividing by negative 4, we get a is equal to 3. And once we have a equals 3, we can now substitute that back in and we can use this to solve for b. And so we'll go ahead and solve for b. And then just like before, once we have a and b, we can plug that into any one of the three equations to figure out what c is. The easiest place to plug it in, however, will be right here. Since we know that c is equal to 9 minus 2a minus b, we could simply plug in the value of b and the value of a, and that will allow us to solve for c. So if I go ahead and make those substitutions, we end up getting c is equal to 1. And we put those together. Our answer, remember, is A, B, C. And this is our solution. So it doesn't matter if you use elimination only or substitution only, or you can use a combination of the two methods to solve these three variable systems. The important thing here is to be neat when you do your work so that you can keep track of all the steps. Because most of the time when people make a mistake solving these, it's because they've made some kind of a simple mistake. All right, so that's it for 3.3. We're going to go on to look at some applications now. So we're jumping to section 3.6, applications of two variable systems. And this is only a single type of application. There are many ways that you can apply two variable systems to solve problems. This one is what we call a mixture problem, and it asks how many ounces of a 25% alcohol solution and 60% alcohol solution must be mixed to obtain 210 ounces of a 45% alcohol solution. So in this mixture problem, you have two different types of mixtures, and they are being mixed together to form a third solution. Each one of these mixtures has a concentration of alcohol, it has a quantity of how many ounces you are mixing, and then it also has the pure alcohol in each mixture. So to help us start off with a problem like this, I'm going to create a chart. Okay, so here's the chart. Let's go over the basics. In the chart, we list the important aspects of this problem. So first of all, we have the type of solution that we are talking about. And in the given information, we know we have a 25% alcohol solution mixing together with a 60% alcohol solution to form a 45% alcohol solution. So the first column I have here is the concentration. So that is the strength of each one of these solutions, which is just the percentage once again, but we need to write it in decimal form. So the concentration of a 25% alcohol solution is 0.25. 60% alcohol solution, concentration is 0.60, and for a 45% alcohol solution, it's 0.45. Next, we have the quantity. How many ounces of the 25% solution are we mixing? It's actually unknown. So I'm going to call that X. How many ounces of the 60% solution are we mixing? That is also unknown, and I'm going to call that Y. And then the quantity of the final mixture, the 45% mixture, we actually know that we want to end up with 210 ounces. And so I put 210 there. And then finally we have the pure alcohol. So when you have a concentrated mixture of a certain concentration and you have a certain quantity, the amount of the pure substance, in this case alcohol, in that mixture is simply concentration multiplied by quantity. So for the 25% mixture, the pure alcohol is 0.25 times X. For the 60% mixture, it is 0.60 times Y. And for the final mixture, it is 0.45 times 210. Now, this is just the initial setup of the problem. We haven't actually done anything yet mathematically, but we are well on our way to getting to this solution. So now, notice that we are trying to figure out how many ounces of each to mix. So ultimately, we want to know the solution for X and Y. That's what we're solving for. To solve for two variables, X and Y, we need to have two equations. One equation is relatively simple. We know the quantity of the 25% solution plus the quantity of the 60% solution must be equal to the overall quantity of the mixture. And so all I'm doing here is I'm adding these variables together to equal the total. Now, in very much the same way, we're going to add the pure alcohol from the two mixtures that are being mixed together, and that should equal the pure alcohol in our final mixture. And so for the pure alcohol, it's 0.25 times X plus 0.60 times Y is equal to, and then 0.45 times 210. So I can use either substitution or elimination. I think I'll go ahead and use substitution. So in the first equation, if I simply subtract X from both sides, we get Y equals 210 minus X. And I'm going to take this expression and substitute it into the second equation, replacing Y. Now also, when I make that substitution, I'll go ahead and multiply out 0.45 times 210. So when we make that substitution, here's what we get. And so now all we have to do is solve this equation for X. So we'll do the math here. We get 0.25X plus, now we have to do 0.60 times 210. And if you do that multiplication, you get 126. And then 0.60 multiplied by negative X is going to be negative 0.60X equals 94.5. And the 94.5 here comes from multiplying 0.45 times 210. So next we go ahead and combine like terms. 0.25x, take away 0.60x is equal to negative 0.35x plus 126 equals 94.5. Subtract 126 from both sides, and this gives us negative 0.35x is equal to negative 31.5. And finally, I'm going to divide both sides by negative 0.35. And that gives us x is equal to 90. Now, once we have x, remember that's only part of the solution. We want to know the quantity of 25% alcohol and the quantity of 60% alcohol that need to be mixed to obtain the result. So x, if you go back to the table, x is the quantity of 25%, y is the quantity of 60%. So we need to know what y is, and to figure that out, we just take our x value here and we substitute it back in. And putting that back in there, we get y equals 210, take away 90, which is equal to 120. And now we can answer the question. X is 90, so that means we need 90 ounces of the 25% solution. Y is 120, so we need 120 ounces of the 60% alcohol solution. And this is our final answer. Now, you will encounter some other types of problems in the homework that are not mixture problems, but they can oftentimes be set up in a very similar way. So I know that you might find some of the problems to be a little bit tedious, perhaps even frustrating, but you need to try your best to work your way through those examples. So we're going to conclude with section 3.7, which is simply applications of 3 variable systems. So it's very similar to what we just did with 2 variables, except that now we have 3 variables. And so here's a problem. Tickets to a soccer match are $5 for children, $10 for adults, and $6 for seniors. There were 465 total tickets sold for a total amount of $3,640. If there were 100 more adult tickets than children tickets, how many of each type of tickets were sold? Okay, so we need to know how many children tickets were sold, how many adult tickets were sold, and how many senior tickets were sold. So what I'm going to do is go ahead and define some variables. I'm going to let x equal the number of children tickets. Y will equal the number of adult tickets. And Z will equal the number of senior tickets. Now, we are trying to solve for 3 variables, and that means we need 3 equations. The first equation is relatively simple. We know there were a total of 465 tickets. So we know that if we add up the children tickets plus the adult tickets plus the senior tickets, that must be equal to 465 total tickets. Next, we come to the value. So the total amount of all these tickets was $3,640. That's the total amount of money collected for all the different types of tickets. To figure out the total amount, we have to multiply each of the different ticket numbers by the corresponding value. So for example, if there were X children tickets and each children ticket is $5, then the total value of all the children tickets sold would be $5 times X. And then the total value for the adult tickets would be $10 times Y, and for senior tickets, $6 times Z. And so we can get the total value by $5 times X plus $10 times Y plus $6 times Z, and that must be equal to $3,640. $2,640. And we can leave the dollar sign off of the equation here. It helps it to be a little bit more streamlined if we do that. So we're not quite ready to solve this system because, as you can see, we only have two equations and we have three variables. So we need one more equation. And here's the information for our last equation. If there were 100 more adult tickets than children tickets, how many of each type were sold? So the number of adult tickets is 100 more than the number of children tickets. So I need to write that as a mathematical equation. The number of adult tickets is equal to the number of children tickets plus 100. Now think about that for a minute. The number of adult tickets is 100 more than the number of children tickets. So notice this third equation does not have the variable z in it. This is actually a good thing. What that means is that we can actually take this third equation, y equals x plus 100, and we can substitute into y in each of the previous two equations. So if I do those substitutions, here is what we're going to get. So I went ahead and made those substitutions, plugging x plus 100 into here, which gives us this, and plugging x plus 100 into here, which gives us this. Now we just need to simplify each one of these equations. So if I remove the parentheses here in the first equation, x plus x is 2x, plus 100, plus z equals 465. And the second equation, if we distribute here, we end up getting 5x plus 10x plus 1,000 plus 6z equals 3640. Simplifying a little bit further, here we have 2x plus z equals 365. And think about what I did there. All I did basically is just subtract 100 from both sides. And for our second equation, 5x plus 10x is 15x plus 6z. And if I subtract 1,000 from both sides, we will get 2640. And you'll notice that I'm starting to skip some of these more basic steps in an effort to shorten the length of some of these videos, because if I show every step for every problem, these videos end up being really, really long. Okay, so here's the resulting system that we have. So now we just need to solve that system for x and for z. And to do this, you can use substitution or elimination. I'm going to go ahead and use substitution. I can take that first equation and solve for z by simply subtracting 2x from both sides. And then I can take the expression 365 minus 2x and substitute it in for z. And if we do that, we get 15x plus 6 times 365 minus 2x is equal to 2,640. And now all we have to do is multiply it out. And so we get 15x plus 2,190 minus 12x equals 2640. 15x minus 12x is 3x. And the rest, and then I'll subtract 2190 from both sides. And this gives us 3x is equal to 450. And finally, dividing by 3, we get x equals 150. So we now know x, which is the number of children tickets. Once we know what x is, we can plug that back into here to solve for z. So if I bring that over here, we have z equals 365 minus 2 times 150, which is 365 minus 300, which is 65. So z is 65. So that means there were 65 senior tickets. Now we just need the number of adult tickets. So you could take z and x and plug it back into one of the original equations. But if you'll notice right here, I can actually solve for y very easily by simply saying y equals x plus 100. And so y is 250. And so now we have our solution. Now our solution should not be listed as an ordered triple. It should be stated as a solution to a problem. So the solution is 150 children tickets, 250 adult tickets, and 65 senior tickets. All right, time to get to work.